Okay, hello Cloud Gurus, and welcome to this lecture where we're going to take a look at all of the networking services in the Google Cloud Platform. Let's say we start with an end user who wants to visit our web app. They might go to their browser and type in mycoolwebsite.com, but for their computer to know what that means, it's going to have to do a DNS lookup, and that journey starts at the domain registrar. Google Domains is aptly Google's registrar for domain names. Amazon includes domain name registration in their Route 53 service, or you might use something like GoDaddy to register your domain name. Now you could definitely use either of those registrars and still host your system on Google Cloud Platform, but Google Domains is an option anyway. A registration with Google Domains includes private Whois records, and you can either use their built-in DNS or point it to your own custom name servers. One nice thing about Google Domains is that it does support the DNSSEC system. Also, if you choose to use their built-in DNS, that includes email forwarding with an automatic setup of SPF and DKIM records. But let's say that you want to use some custom name servers. In this case, as the registrar, Google Domains will point to the name servers you've set up. And that's where Cloud DNS comes in. Cloud DNS is a scalable, reliable, and managed authoritative domain name system service. In Amazon's world, DNS is handled by the Route 53 service, which makes sense because DNS lookups happen on port 53. Now, if you didn't go with Google or Amazon, you might consider using a service like Dyn, because running your own DNS servers is generally not a good idea for most people. Cloud DNS has a 100% uptime guarantee. Google has built and manages this system so that it should never fail. There's a lot of redundancy built in structurally. Now, when you do use Cloud DNS, it distributes your DNS records all around the world so that there's very low latency lookups. And like Cloud Domains, this also supports the DNSSEC system, so that when people's computers are trying to figure out where your servers are, they know that the pointers they're getting are authentic. Now, you can manage the DNS records that you set up through either the UI, a command line, or API calls, and you pay a fixed fee per hosted zone to store and distribute those DNS records around the world. You also do pay an amount for how many lookups are done against those DNS records. Now, in the end, those DNS lookups are going to result in an IP address so that your user's computer or device knows where to connect to find your website. And that's where GCP's static IPs come in. You can reserve static IP addresses in GCP projects and assign them to different resources. This is a lot like Amazon Web Services' Elastic IP address. Now in GCP, there are two kinds of static IP addresses. There are regional IPs that you can use for Google Compute Engine instances and network load balancers, and there are global IP addresses that you can use for the global load balancers, those being HTTP, HTTPS, SSL proxy, and TCP proxy. These Anycast IPs at the global level really simplify DNS, because instead of the DNS servers having to know about the target or pointing to some sort of a service, you can just put in a DNS-A record that any DNS service can handle. Now, these static IP addresses don't generally cost anything, but they will if you hoard them. You pay for reserved IPs that are not in use, because the public IPv4 address space is a scarce resource, so we shouldn't waste them. So let's say that we are using one of these static IP addresses, and we're pointing it at a load balancer. That's where Google's Cloud Load Balancing comes in. Google's CLB offers high-performance, scalable traffic distribution that's integrated with auto-scaling and Cloud CDN. Outside of GCP, you might compare this to AWS's Elastic Load Balancing, or if you're doing this on your own, you might use HAProxy or Nginx. Now that said, Google's Cloud Load Balancing is not quite like those others. It's special. This cloud load balancing is built into their software-defined networking system, so it can naturally handle spikes without any pre-warming. There aren't any instances or devices that are sitting there provisioned waiting for your traffic. Now, if you see any references to Google's Andromeda, that's their networking system, and this is built on that. Cloud load balancing is highly integrated with Google's global network, so when you have an IP address externally that's pointing to Google Cloud Load Balancing, it comes to Google's network anywhere that's closest to it around the world. So the first benefit of this is that there's low latency to connect to the load balancer, and then you maximize the distance that network traffic travels within Google's fast private network, and we'll take a closer look at this in a little bit. Now, the regional network load balancer can do health checks to make sure that wherever it's sending data is ready to accept it. And although it normally just round robins incoming requests to the different targets, you can also set it to have session affinity so that all of a particular client's requests will go to the same target. Now, when you set this up, the forwarding rules are based on the IP address and protocol, and if you want to, they can also be based on the port. The second type of load balancer is the global one. Now, the global load balancers are where it gets really interesting, because you can set up things like multi-region failover. So remember how I said that the IP address points to a particular load balancer? Well, since the load balancer isn't instances or devices sitting somewhere, since the load balancer is actually built into Google's networking fabric, then when the request to a particular load balancer hits the edge location of the Google network, Google makes decisions right there of what to do with that request. So even though this global load balancer has one IP address across the world, it'll automatically direct traffic to the region closest to the user, so that that user will get the lowest latency connection possible. And if that region reaches capacity or fails somehow, then the load balancer will just redirect new connections to another region with available capacity. And because this logic is built into Google's networking system as opposed to something that happens on the client machine through something like DNS, this can react really quickly to changes in the user's traffic, network, and the health of systems. This is a really powerful system, and it's one of the ones that shows off how global the Google Cloud Platform really is. So the way that you pay for cloud load balancing is by making your ingress traffic billable in addition to your egress traffic, plus effectively an hourly rate per load balancing rule that you set up. So let's say that your end user's device has managed to reach this global cloud load balancer. One of the rules you might set up is to direct that incoming request to Cloud CDN. Cloud CDN is a low-latency content delivery network based on the HTTPS Cloud Load Balancer that's integrated with Google Compute Engine and Google Cloud Storage. Now you might compare Cloud CDN to services like Amazon CloudFront, Akamai, and Cloudflare. Cloud CDN supports HTTP2 and HTTPS, but it's important to note that this does not support custom origins. You can only have Cloud CDN get its data from within the Google Cloud Platform. When you're using an HTTPS load balancer, this is super simple to turn on, just a simple checkbox. So Cloud CDN caches data at its CDN locations all around the world, but when a user requests some data that isn't available at the cache already, you wind up with a cache fill request that results in some network egress charges from your origin back to the point of presence. So once that data has made it from the origin to the point of presence, it'll be cached there as appropriate, and then both the initial request and all subsequent requests will result in an egress charge from the point of presence to the client, and those charges vary by location. You also pay a bit for the volume of requests that are made to your Cloud CDN distribution. And if you want to get rid of stuff that's cached at the points of presence before those caches expire naturally, then you'll pay a charge per invalidation request too. Of course, you'll also pay normal usage charges for the origin, but this can be dramatically lower if you have a good caching strategy. Now, if you're not connecting to the CDN, you're connecting somewhere else in GCP, and that will happen through the Virtual Private Cloud. The VPC is a global IPv4 unicast software-defined network for GCP resources. So the really key thing here is that it's a global software-defined network. Software-defined networking lets you do a lot of interesting things that you couldn't reasonably do in hardware devices, and Google's approach to it is quite powerful. Now, this virtual private cloud definitely compares to Amazon's VPC, but it's also quite different in a few important ways. And if you were looking to get this kind of capability on your own outside of the cloud providers, you might see what you can do with OpenFlow. So there are two modes for the virtual private cloud. The automatic mode is really easy. It's automatic, and you don't really have to do any setup for it to be useful. But if you need a lot more control, there's a custom mode that gives you that. You can configure subnets, each with their own private IP range, routes, firewalls, VPNs, border gateway protocol, all sorts of things. Now, the VPC network itself is global, and each subnet is regional. Note that subnets are not zonal, they're regional, which means that you could have Google Compute Engine instances across multiple zones in the same subnet. This can simplify your configuration somewhat. VPCs can also be shared across multiple projects in the same organization, and they can be peered with other VPCs, including ones outside of that organization. Another feature is that you can enable private access to some GCP services, which means that they'll use their internal IP addresses to connect to them. Now, the VPC itself is free to configure, but you'll pay to use certain services within it, and of course for the network egress charges that we've already talked about. Now let's say that the client request that we've been following along with has gotten to some Google Compute Engine instance, but the app that's running there needs to make a request back to one of the business systems running in your own data center. This is where Cloud Interconnect comes in. Cloud Interconnect is the set of options for connecting external networks to Google's network. Now you can make private connections to a VPC through the Cloud VPN or dedicated interconnect services, and they come with service level agreements. Alternatively, you can connect to public Google services, including GCP, via the external peering services, which don't come with SLAs. Now, direct peering is something that you might set up if you can meet all of Google's peering requirements, but if you can't meet those requirements, then you can connect via a partner to carrier peering. Now, a key benefit of Cloud Interconnect is that you have significantly lower egress fees, except Cloud VPN, which stays the same. So speaking of Cloud VPN, this is an IPsec VPN to connect your VPC via the public internet for low-volume data connections. This is rather similar to Amazon's VPN, and if you were doing this on your own, you might look at using OpenVPN. This is for persistent static connections between gateways, so it's not really for a road warrior dynamic client type situation. In particular, the peer VPN gateway has to have a static IP address that you can connect to. Now, Cloud VPN connects to one particular subnet in your VPC, and the link into that subnet is encrypted, which is a bit different than dedicated interconnect, which, although it's a private connection, doesn't actually encrypt that traffic. Now, when you're setting up the networking for Cloud VPN, you can set it to either have static routing or dynamic routing, and in general, dynamic routing is preferred so that you can make changes without having to recreate the connection. Cloud VPN has a 99.9% availability agreement, and you pay for however long it's connected and whatever the normal traffic charges are. Now, dedicated interconnect is a direct physical link between your VPC and your own data center for high-volume data connections. This is quite similar to AWS's Direct Connect. So a VLAN attachment is a private connection to your VPC in one particular GCP region, and you can't access any of the public GCP APIs through this. So dedicated interconnect is not really multi-regional in the storage sense, like those resources might move around amongst those regions, rather that there are a set of GCP regions supported by each particular interconnect location, and you choose from one of those for each VLAN attachment. Now, the links are private connections, but the traffic's not actually encrypted, so if you absolutely need to encrypt all traffic in flight, you can layer your own encryption over top of this. If you have critical applications using this dedicated interconnect, Google recommends that you have redundant connections in different locations. That way you can achieve 99.99% availability guarantee. Otherwise, the SLA gives you 99.9%. So for dedicated interconnect, you pay a fee per 10 gigabit per second link you set up, plus a relatively smaller fee per VLAN attachment. And then you pay reduced egress rates from the VPC that go through the dedicated interconnect. Now, the cloud router is related to these systems in that it offers dynamic routing across these links using the Border Gateway Protocol. Now, this works with both Cloud VPN and dedicated interconnect, and it automatically learns the subnets in your VPC and announces them to your on-premises network. Without the cloud router, you have to manage static routes, and so changing the IP addresses on either side of the VPN connection requires you to recreate it. Cloud Router is free to set up, but like usual, you'll pay for the VPC egress charges. One more connection to talk about is the CDN interconnect. This offers direct, low-latency connectivity to certain CDN providers with cheaper egress rates. Now, this is for the external content delivery networks, not Google's Cloud CDN service, and it supports Akamai, Cloudflare, Fastly, and others. Now, you'll get these cheaper egress rates for both pull and push cache fills because it's all about the traffic with that CDN. You set this up for a particular GCP project and particular GCP regions, and it's free to do that, and then you'll wind up paying less for the egress that you've configured. So you really should do this if you're using an external CDN. Well, that's the look at all of the networking related GCP services. If you have any questions, please let me know. If not, please feel free to move on to the next lecture. Thank you.